This is Mr. Potter. In our previous lesson, we talked about improper integrals, the idea that I could try and evaluate an integral of some function that has a specified behavior from some point to infinity. And I can try and figure out what this integral is equal to by using a limiting technique, using a limit and finding the antiderivative function, just using the end function behavior to determine that. The thing is, this is one type of improper integral, but in fact there's actually several types of improper integrals. Now, I'm hoping to go into today's lesson to talk about some of those other types of improper integrals. So one of the things I wanted to start off with is I'm not necessarily dealing with when my boundary is undefined because my domain is undefined. I'm going to actually take a very simple idea here. I want to take a look at the integral from a to 4 of 1 over radical x dx. So this is just x to the negative 1/2, and when I find the antiderivative of that, that's going to end up with 2x to the 1/2 power, which I'm going to evaluate from x equals a to x equals 4. And this is something I can substitute in fairly simple. I'm going to have 2 times the square root of 4 minus 2 times the square root of a, and this ends up being 4 minus 2 radical a. So pretty straightforward substitution. The thing that's interesting is that in my original problem, x equals 0 was not in the domain, but in my antiderivative, x equals 0 now suddenly is, which means I can go from trying to evaluate this antiderivative to trying to find this definite integral, the integral from 0 to 4 of 1 over radical x dx. And I can do that by just taking a limiting technique. The limit as b goes towards 0 of the integral from b to 4 of 1 over radical x dx. Well, we just solved this. We found that this was equal to 4 minus 2 times the square root of my limit variable. And if I'm taking a look at the limit as b approaches 0, this ends up just being 4. So I know what the graph of y equals 1 over radical x looks like. It has an asymptote at x equals 0. It tends to go towards infinity, but it doesn't, it doesn't go towards 0 as quickly as 1 over x is or 1 over x squared does. And so what I'm saying is that if I want to find the area from 4 0, and of course this is unbounded, I'm still going to have that situation where I can find the antiderivative, and I can actually substitute in the antiderivative because x equals 0 is in the domain of my antiderivative function, even though it may not be in the domain of my function that I'm trying to integrate. And so this brings up a very interesting point. The question is, what actually makes an integral an improper integral? The whole idea here is that if any point in the domain and I'm using the word point here a little loosely because this could possibly deal with infinities. But if any point is in the domain, then we can just substitute. But if the point is not in the domain, then we need to take a look at this from a limit standpoint. And so a lot of the ones that we've had that have worked have been situations where either the antiderivative, in other words, if my function has an antiderivative, I can either substitute in a particular value, or I can look at it from a situation, and the idea is that this exists. So either the limit's going to exist, or I can actually substitute because it is an element of my antiderivatives domain. Even though this wasn't necessarily a point in my original functions domain, even if we're talking about at x equals infinity. So this brings up an interesting idea that I can find the improper integral if I have just any quirk in my domain. And of course, we learned that there are three things that mess with our domain. Dividing by 0 messes with our domain. Taking an even root of a negative number will violate our domain, and also taking the logarithm of either a 0 or negative value. So I want to do one last example here. This will be a pretty short lesson, but I want to do a doubly improper integral. And by doubly improper, that means that I really need to take a look at this from two different sides. So I'm going to start off with this function. I want to find the integral from 0 to 3 of x minus 2 to the negative 2/5 dx. So I'm looking at this, and x equals 2 is a problem because it's not an element the domain of my function that I'm trying to integrate. So I really need to treat this as two separate problems. I need to treat it as the integral from 0 to 2 of my function. And the integral from 2 to 5 of my function. Now all I'm doing at this point is I'm using one of the properties of integrals that we talked about. The idea is that if I have an integral on a domain, all I need to do is to break it apart into its two components or multiple components. The reason that I'm breaking it apart at x equals 2 is because x equals 2 is my problem. What I'm going to have to do is, instead of taking the integral from 0 to 2, I'm going to have to take the integral from 0 to a and let a approach 2. That's how I'm going to be able to find this integral to the negative 2/5 power. And over here, I can't do from 2 to 3. I'm going to have to do the integral from b to 3 of x minus 2 to the negative 2/5 power. And I'm going to have to take the limit there as well. The thing is, anything that's involving my 2, anything that's involving this issue with my domain, I really need to treat it from a limiting standpoint. And just to be clear, I'm really looking at this being a limit from the left, and I'm looking at this being a limit from the right, because this function may not have an actual limit at this point. As a matter of fact, I have a vertical asymptote at x equals 2. So if I want to try and evaluate each of these integrals, I'm going to have to take a look at it from a limit standpoint. And that's why I'm calling this a doubly improper integral, because I actually had to break up this one domain into two integrals, each of which is an improper integral. So this is a power, so I'm going to use the power rule. So I'm going to increase the exponent by 1. That's going to make my exponent 3/5. And then I'm going to divide by my new exponent, which makes this 5/3. And I'm going to evaluate this from x equals 0 to x equals a. And then take a look at the limit as a approaches 2 from the left. And whatever I'm going to do, I'm going to add that to this 5/3 times x minus 2 to the 3/5, evaluated from x equals b to x equals 3. The limit is b approaches 2 from the right. Now at this point, notice 2 was not in the domain of my original function, but 2 is now in the domain of my antiderivative. So in other words, x equals 2 is perfectly fine to substitute in this point, because 0 to a power that's positive gives me 0. But 0 in the denominator is a much more troublesome thing to work with. At this point, I can actually substitute. So here, I mean, technically I am still taking the limit as a approaches 2 from the left, but this is going to be a minus 2 to the 3/5 minus 5/3 times negative 2 to the 3/5. And I'm going to add that to substituting in b and 3 over here. 5/3 times 3 minus 2 to the 3/5 minus 5/3 times b minus 2 to the 3/5. Again, remember this is a limit as b approaches 2 from the right. But here, if a is approaching 2, this term actually ends up being 0. And similarly, if b is approaching 2, this term ends up being 0. So what I've got is I've got 3 minus 2, which is 1. 1 to any power is 1. And 5/3 times 1 is 5/3. Minus, over here I've got 5/3 times negative 2 to the 3/5 power. And of course I can factor out a 5/3, but more than that, I can take this negative out because it's an odd power. And this actually ends up being 1 plus 2 to the 3/5 power. And so what's happening is I have this function that has an asymptote at x equals 2. And even though this function has an asymptote at x equals 2, even though my function has that asymptote, I can find the area from here to here. I can find this area, unbounded as it is, infinite. I mean, no perimeter here. I mean, I've got an undefined perimeter, but I've got a finite area here. This 5/3 times 1 plus 2 to the 3/5. So I have a way of trying to evaluate the area, even though I really have an asymptote on either side. My area is kind of cut in the middle by an asymptote. And I can do this through the power of improper integrals. But in order to deal with this, I'm dealing with limits involving infinity. So that concludes chapter 4. This is Mr. Potter. Thank you very much for watching. Have a great day.